My name is Shaikha, and today we will be discussing the simulation study carried out on natural ventilation. I will start by sharing the project brief and objectives, then information on cross-ventilation. I review the site location and climate, disclose the building materials, share how the model was set up, and discuss the base case and the different strategy approaches. And finally, I reveal the findings and results and conclude by proposing ideas for smart building solutions. We were required to design a building based on an assigned plan and city, and the task was to rely on natural ventilation in the summer to cool down the building. We had to assign a base case and then look at 3 different strategies to improve the air circulation and influence the occupants' comfort without any mechanical intervention. Cross-ventilation is one of the most common forms of passive ventilation for a space, one that uses wind to bring the air through the building. It works by having wind enter through an opening and allowing the air to flow in and out through another opening. Some of the key factors for good and effective cross-ventilation is the size and orientation of the building. In general, narrow buildings tend to have better cross-ventilation. It is difficult to distribute fresh air to all portions of a very wide building using natural ventilation. To help orient your building, we have to look at the prevailing winds for our site throughout the year. And placement of openings is very essential. There needs to be a minimum of 2 openings, such as windows, sliding doors, ventilation louvers, or operable skylights, and they must be placed adjacent or opposite each other on walls of the space. The openings must be able to be opened and closed by the occupants, as there will be a need for adjustment depending on wind conditions at different times of the year. My plan was situated in Manchester, and the location for the 2-story building was identified in a green open space area with no obstructions. The building's use is for a clinic with a total area of 126 meters squared. Based on weather data, in Manchester, the summers are comfortable and partly cloudy, and the winters are long and very cold. In order to select the optimal orientation, different angles were modeled through IES's Suncast, and based on the results, a 180 degrees showed the lowest total energy throughout the year and was selected. Through the template manager, the building materials for the roof, wall, windows, and the floor were selected based on achieving the minimum required standard of the UK's Green Building Code, GREEN. The thermal profile and model setting for the base case was set up to have the heating and cooling on during the entire year, and with lighting as the internal gain and 50% of the openable area for the external window. As for the purpose of the comparing effectiveness of cross-ventilation during the summer, the thermal profile and model setting had the cooling and heating off during the summer for the months of June, July, and August, but had them on during the other 9 months. Therefore, the only energy accounted for during the summer is from the plugins and lighting. Upon running the model of the base case, the comfort index looked to be between 4.8 and 5. As my natural ventilation mechanism is cross-ventilation, the 3 strategies identified are on the number of windows, the shape and placement of the windows, and increasing the open space of the layout. For the first strategy, Scenario 1 looked to increase the number of windows from 1 to 2 compared to the base case, and have had them adjacent to each other. For the second scenario, the number of windows increased, and they were placed both adjacent and opposite of each other. In the third scenario, the windows were added by the ends of the corridors in order to set up additional inlets and outlets for air to enter into the floor. Looking at the results, there has been an increase in total energy, but that increase was not during the months of June, July, and August. Upon running the CFD for the 3 scenarios of Strategy 1, it appeared that the velocity, temperature, and pressure had minimal changes throughout the different scenarios, with the velocity ranging between 0.02 to 0.12 meters per second, and the temperature ranging between 16 to 20 degrees Celsius, and the pressure ranging between negative 0.18 and 0.219. As for the second strategy, we explored with the shapes and sizes of the window in order to try different placement and their effect on the building. Upon reviewing the results, it was noticed that the values of the velocity pressure, and temperature did not significantly change. Looking at the total energy, we have selected scenario 2B to take forward into the third strategy. Looking at the solar gain results, it was noticed that with the increase of the size of the windows, the total solar gain increased. Coming to the third strategy, and in order to further enhance the effect of cross ventilation, we looked into adding windows on the top of the doors of the exam rooms, since 4 of the 6 had only one window placed, and we wanted to analyze if this would have an effect for scenario 2. For scenario 2 of the third strategy, we removed the door and replaced it with a void, and we also replaced the window at the top with a void. As for scenario 3, we only allowed for a short wall partition for each room in order to increase the air circulation allowance. Running the simulation, the total energy dropped with the removal of the door and the window. We also noticed that there was a change in the velocity and pressure between scenario 1 and scenario 2. The maximum velocity slightly increased from 0.13 meter per second to 0.15 meter per second. As for the pressure, the difference of the range decreased. The temperature remained unchanged between the scenarios, but we did notice that it became slightly warmer compared to strategy 1 and strategy 2. Also noticeable that with the increase of the void, the solar gain dropped with each scenario running. Coming to the final results, it was evident that the external velocity and external pressure did not change throughout the different strategies, and that is due to the fact that the exterior shape of the building did not change. We did not greatly exceed the final total energy of the building compared to the base case, as the base case total energy was 16.0499, and the final design of the building's total energy was 16.8442. We saw more results between strategy 1 to strategy 3 and strategy 2 to strategy 3, but that's when it comes to velocity, temperature, and pressure. There was barely any changes between strategy 1 to strategy 2. What we can deduce out of this is that cross ventilation can be highly effective with more open spaces. The comfort index has reached 8, but looking at the readings for the whole summer, we can see that at some points the temperature does drop to 15 and 16, which drops the comfort index. Therefore, and although it's in the summer, the UK can get a bit cold and heating will still be required. Smart technologies leverage processes that ensure the indoor environment is not adversely affected by the external aspects. It seeks to synchronize the designs and control processes that maintain optimal temperature, ventilation, and lighting, among other aspects. Building automation and building energy management systems can help a clinic in a 2-story building by increasing the staff and patients' well-being. Energy consumption and ventilation are optimized to ensure that almost zero tolerance to residual ventilation or energy consumption. Through an intelligent system based on a single operation platform, it will be possible to monitor each medical unit's energy requirement and hence ensure energy is supplied on a needed basis. This system will also form the basis of ensuring that lighting, cooling, and ventilation are availed as per the space's occupant requirements and localized to avoid wastages. The system will ensure that the clinic's activities remain unaffected even during adverse weather. It will also form the basis for saving energy by ensuring use where needed, at the required amount and duration. It will also allow to know when and how many escalators or elevators are in operation to avoid energy wastage. Thank you for listening.